project. I'm Richard and today I'm going to look at op amps. Now this is my first look at op amps, so I'm going to keep it nice and simple, and instead of looking at the whole package and dissecting it and trying to work out what the whole thing does, I'm going to look at specific uses of the op amp so I can try and understand the different parts about how it's operating, starting with the buffer. Now it doesn't sound like it's doing much, and I don't think it really is. Effectively what you put in is what you get out as far as the voltage goes, but I think there are some other major or important factors about that buffer. So let's start by having a look at the actual diagram, the actual circuit I'm going to be using, and then we'll move on from there. Okay, so here we have my little diagram. It's a basic circuit, one op amp. I'm going to use the LM358 to do this. There's a reason why I'm using this, I'll show you later. Resistor on the output, that's going to be a 1k resistor, and it loops back around, as all buffers should, my output to my inverting input. My non-inverting input is just basically, well, I could have put just a resistor divider here with one of them being a pot and making it work as a variable resistor. But what I've decided to do is to use an LED. Why? Well, because it doesn't turn on straight away, so the current will, as it were, lag behind the voltage, and also it's a reference. It's something you can see. It's a visual thing, so it's great to be able to see it actually working. And then what I do is I just trim this 1k pot that I've got. I'm going to use a 220 ohm resistor. Why? Well, because it's just nice to have something in front of that LED. But what I want to see is the voltage at that point before it goes through the LED. And I'll have a look at the output to see what that is in relation to that input, because this is supposedly a buffer. What you put in is what you get out. So yeah, let's have a look at that on the workbench and see what's actually happening. Okay, so I've got my setup here on the breadboard. 2 multimeters. Let me I'm just going to push this up and see if I can just zoom in. No, wrong way. Yeah, let me just see if I can get this properly in shot before I turn it on. Wrecking the joint doing this. Okay, so first of all, it's a little circuit. You've got the LM358 there. I've got a 741 here, which I'm going to have a look at in a little bit, but let's focus on this one first. There's my input. That was that little trimmer pot, resistor, LED, and that's where my input is. And then the output, well, there's a little resistor here, and that's what we're testing. So let's start with the voltages. Let me just get this all back into shot. Now I've messed around with this. I had got it set perfect, and I've moved everything, but yeah, well, all that back down and get the multimeters in shot, because that's what I'm after. Drag that back down. I ought to mark this up really so I know exactly where centre is. Never mind. Now, yeah, without shorting anything out, if I can. Right. But you can still see this because there's the LED there, and you'll be able to see that come on when it comes on. Okay, input, that's my voltage there. Output is my voltage there. So as a buffer, supposedly they should follow each other. I should get the same output as I have input. I'm going to use 5 volts for this. Turned it on, the pot's all the way down, so I've got nothing. So if we turn this up just nice and slowly, as you can see, the LED hasn't come on yet, so that hasn't turned on. It will turn on at a particular point, but my output is mirroring my input. And there you go, LED is just starting to come on. It's just starting to light up, and as I turn this up, it gets brighter and brighter. But the output has followed the input. What I've got out is what I'm putting in. So the voltage, as a buffer, they will follow each other, which is brilliant. Now, what about the current? So I suppose I better swap these multimeters around and have a look at the current and see what's going on there. So now I've swapped over the multimeters, so this is now looking at the current. This one is looking at the current at the input, so it's before the LED, so we're going to see what's going through that side, so that's what's coming across the input, and this is going to look at the current before it goes into the resistor on the output. So let's turn it on and turn up the voltage. Actually, look at that, I'm getting slight current already on the output. If I wired it up the right way, and as I turn this up, I'm getting a greater voltage on the input, which again we know directly reflects the output voltage. So effectively I'm just turning up the output voltage, and the current is going up and up, but the input current, there's nothing there, nothing at all. So what's connected to the output is determining what current it's going to get. I might have to change this up a range. There we go. So the output's got a lot of current and the input hasn't got any, and it effectively shouldn't have any current at all until the LED turns on, because until that junction, which is basically a type of diode, an LED is just a light emitting diode, until that junction turns on there isn't any current flow at the input, and yet as you can see the output is getting current. So that would have to be, yeah, that is showing that the output is not a reflection of the input when it comes to the current. They're isolated. The current flowing in the input is only flowing because the LED is determining what current is going to be flowing. It doesn't actually go into the op-amp, whereas the output is from the op-amp. The op-amp is supplying that current to that resistor. So what I'm going to do now is I'm now going to do it, change the multimeters over, so one will be looking at the voltage and one will look at the current. So I'm going to start off with the current on the input and the voltage on the output, and then I'll swap them round. Right, so now that I've changed these multimeters over, I'm now just looking at the output stage, just the output. So this is my voltage output and this is my current output. So if I now turn this up, what we see is that they appear to be matched, but actually this is in the 20 volt range, so I've got 1.2. Let's say if I could get that to exactly 1 volt. Not quite, no, never. A bit twitchy these pots, but if I could get that to exactly 1 volt, I've got exactly 1 milliamp there. Now that works because I've got over here a 1k resistor. So if I've got 1 volt on my output across a resistor and I've got 1 milliamp showing, I've got 1k resistor. And if you say, if I've got 1 volt divided by 1000, I get 1 milliamp. So that is a perfect example that the output is the output current is dependent upon the load. Whatever I've got in here, that load is going to determine what current I'm going to have on the output. And as I've got 1 volt currently on the output, which would be the same as the input, it'd have 1 volt, my current across a 1000 or 1k ohm resistor is going to be 1 milliamp. So yeah, the output is determined by the load, not by the input current. So let's have a look at the input. Now I'm looking at the output stage, the input stage. This is looking at the current and this is looking at the voltage. Now, as we've determined, the voltage is the same on the input as it is on the output. But let's have a look at this current and see how it differs from the last one. As you can see, because I've got an LED in here, it won't turn on until it reaches a particular point. It would work just as well with a diode, but an LED lights up, so that's what I'm using. As I said before, it's a nice visual reference. And as you can see, as I turn it up, I'm getting no current on the input, despite the voltage on the input going up. And I know that the voltage on the output is the same as this. And yet when we did that just now, you could see that the current rose in proportion to the voltage input, depending upon the load. On the input, it doesn't do nothing. There is no current flow effectively on the input until the LED starts to come on. As you can see, it's just lit up now. So as I turn that up, I get more current flow. The voltage near to what it's going to take, because there's a resistor in front of that LED, so the LED is just going to come on at whatever voltage it wants to work at. And in this scenario, I've now got 2.66 volts across the LED, and we're drawing just over 1 milliamp, which is brilliant. The LED is nicely lit, but it does show that the voltage will follow, but the current is dependent upon effectively the input load, what you've got there to determine the voltage. That current doesn't go into the input, and from all these different experiments, it seems to show me that that is exactly what's happening. My voltage is the same on the input and the output, but my current is determined on where, basically for the input and the output, my current is determined by whatever those loads are on the input and the output. They're not the same. They're independent of each other. They're isolated. They are buffered from each other. So that works just fine. Dear me, that is brilliant. That does exactly what I want it to do. I suppose the other thing I could have a quick look at is the LM741, which I've got here. Will that work as well? I don't know. Let's have a look. So now I've wired it up differently. Well, not really. What I'm looking at is the voltage on the input against the voltage on the output. The only difference is that now I'm using an LM741. And now we're going to see if there's a difference between op amps. Hey, will you look at that? Nothing on the input, but I got 1.9 volts on the output already. I haven't done anything. I haven't turned this pot up. So let me start turning this pot up, and the voltage comes up on the input. But I'm not affecting the output, which is a bit odd. See, the LED is starting to come on, starting to get light going, so obviously that's now passing current. But as we've established, the current on the input is not the same as the output. It's determined by the load, but the voltage isn't following. So what's going on there? I'm not getting what I'm expecting to get. You know, this is, that LED's a bit pants, isn't it? Let me just whip that red one out, put that blue one in there. That blue one lights up nicely. Like I say, 1.9 volts, but the input is changing, and all of a sudden the LED springs to life. and then near the end, as you can see, it does match, but as I take it down, this voltage goes down, but it's only when it's above 1.9. So there we have that special thing of op amps that I always have to be careful of. The voltage rails. The LM741 obviously works very well with a dual voltage rail or split rail or whatever you want to call it. Basically you'd need a voltage, plus voltage on the on the input. That's not right, is it? I'm talking rubbish. What I should be saying is that the supply to the actual op amp for it to work, so you can actually use it effectively on this LM741, is that you need a plus voltage and a minus voltage. Without it, the LM741 reaches its limit, its lower limit, which is, it looks like 1.9 volts. I expect its upper limit's probably not too far from that neither, because I'm only using 5 volts. So with this, there might only be 1.5 usable voltage that it can move up and down. Look, you know, as I go up, it can only go up, it'll only go up so far. And imagine if I had more voltage, this would only go up so far until it reached an upper limit. You can get op amps that are rail to rail, whereas with the LM358 it's actually designed to work with a single rail. It actually says in the notes in the data sheet that it's wired internally to ground. So the LM358, even though it'll have the same limitations at the top end, it won't be able to go all the way to the 5 volts, it can come all the way down to ground, which the LM741 can't. So as you can see, not all op amps are created equally. They are different for different applications, obviously. Brilliant. Well, that does seem to work. It's a buffer, it's simple, it's great, it's effective. So with all my testing done, what have I learned? Well, firstly, not all op amps are created equal. There's a wide variety of op amps depending on the use and what you want to use them for, how you're going to implement them, how you're going to power them, single rail or split rail. Now, as a buffer, in the setup I got, the LM741 was rubbish, didn't work, didn't do what I wanted it to. But the LM358, what the 358 was it? Yeah, the LM358 worked perfect, did exactly what I wanted to, which is great. So no need to worry about that. Now, as a buffer, the LM358 allowed the non-inverting input to be equal to the output, or the output equal to the non-inverting input, whichever way you want to look at it. But the current was different. The current was effectively isolated. What was on the input was not reflected on the output, which is brilliant, because that's, I suppose, the purpose of the buffer. It allows one side to be isolated from the other, but still gives you continuity. So I suppose, let's have a look, if you had it in an audio circuit, it would work great. You could use it in audio circuits. I suppose that's where the LM358 comes in quite well, because a lot of audio circuits don't have a minus rail, or let's say a car stereo. It's only got 12 volts, so there's no ground. Well, the ground point is not a minus usually, so you've got a single rail. So you could put an LM358 in a stereo, or that's for a car audio. Brilliant. What else could you use it for? I don't know. I mean, there's lots of uses, isn't there? So have a look at that, have an experiment. I will certainly be experimenting with the thing for other circuits. I suppose the other thing is that as a buffer, it isolates one part of a circuit from another. Let's say with audio circuits, sometimes you need to do what they would call impedance matching, because one part of the circuit can affect the next part if you don't get the impedance match right, because you don't want to drag down the next stage, or you don't want the next stage to influence the previous stage. So a buffer will work really well for isolating those two stages. What more can I say? Buffer. It's a very simple circuit, but very effective, and does some quite important things really. There you go, a buffer. Anyway, if you like this video, give me a thumbs up. If you didn't, you know what to do. Subscribe, and all comments are welcome. See you next time.